All right. Hello, everybody. Welcome to the session on neuro, brain, and medical data. My name is Johanna Bayer. I'm your session chair today. So we have 6 fantastic talks lined up, 3 in person, 3 virtual. As usual, please submit your questions on Slido. Our first speaker is a virtual presentation with the title MV squared net, multivariate, multi-view, brain network comparison over uncertain data. The speaker is Lai Shi.
Hello everyone, we're presenting MV2Net, a visual analysis system for brain network comparison. This is joint work by a team from several research institutions. First, an introduction of the background. Human brain networks have been measured at multiple scales via many different technologies, for example, EEG, MRI, and LM. Our work focuses on MRI data, a non-invasive imaging method for the microscopic level human brain networks. Notably, microscopic visualization over MRI data can support connectivity, individual, and group-level structural brain network visualization. In detail, the structural brain network construction over MRI data relies on 3 major components: the original T1-weighted MRI data, and the corresponding DTI data and the Gero label template. After the brain networks are constructed, we consider a fundamental research problem: the comparison of brain networks between subject groups, including age, gene diseases, because the potential biomarkers for neurology diseases are of great realistic value. We focus on comparing the diseased subject group with the controls, notably Alzheimer's disease. Given this background, we consider specific challenges to the brain network comparison. First, brain network data generally contains huge uncertainty due to measurement errors in brain imaging and network construction errors in registration. Second, the connectivity feature displayed on brain network visualization is generally assumed to be univariate, the connectivity strength or the number of fibers. Third, state-of-the-art brain network comparisons mainly adopt a single-view approach that compares only 2 subject groups at a time. To validate these research challenges in the real-world setting, we conducted pilot studies with domain experts. The pilot study result can be summarized into several key user requirements and corresponding visualization tasks. First, the uncertainty issue in brain connectivity data is important and could potentially be resolved by visual data quality analysis methods. Second, the brain network connectivity should be studied in multi-perspectives. Third, the comparisons beyond 2 subject groups are potentially useful. A similar problem of brain network comparison has previously been studied, which can be categorized into 2 types. In brain network visualization, traditional relationship metaphors have been adopted, such as node-link graphs, node tricks, and the novel visual representation. These are plain visualization solutions without machine learning models to extract and augment discriminative connectivity features. Meanwhile, microscopic brain connectivity visualizations, such as neural lines and abstractocyte, visualize connectivities at the neural level and do not relate to their macroscopic brain networks. The recent work of visual neuro is similar to our work. However, the main problem of multivariate brain network comparison and the data uncertainty issues studied here are not considered in visual neuro. In other types of related works, visualization techniques for network comparison or comparison in general have been intensively studied previously. Existing methods from the neuroscience community mostly compare the brain networks of individual subjects, but cannot reveal group-level differences. The visualization community's group-level brain network comparison methods are limited to comparing only 2 subject groups. To tackle the aforementioned research challenges, we propose a visual analytic system, MV2Net, the multivariate, multi-view brain network comparison method over uncertain data. The pipeline of our system is composed of 4 stages: constructing structural brain networks, the network analysis, the visualization with multiple new designs, and the user interactions to an overview of the corresponding visualization interface, including subject group selection, visual feature quality analysis, group-based brain network comparison, high-order visualization of multiple comparisons, 3D fiber tract visualization. First, beyond the classical single connectivity feature of fiber strings, we also extract multiple diffusion and geometric features from the white matter pathway among ROIs of the human brain. They include popular DTI metrics, as well as geometric features of fiber length, curvature, torsion, and entropy. To understand the data uncertainty for brain network visualization and comparison, we studied the distribution of feature values on the same network connectivity of all subjects. It can be found that a lot of connections are full or non-connections with few non-zero feature values. We propose a measure of feature quality called quality for comparison, which is defined based on the Grubbs test result on the feature value distribution. Based on the measure, we designed an aggregated heat map visualization to display the distribution of all feature values by network connectivity and subjects. An interactive data wrangling mechanism is applied so that users can filter on the heat map to select valid connectivity features according to the percentage of valid feature values. Our system combines effective analytic models to detect discriminative connectivity features that are most different between the subject groups under study. Both univariate and multivariate features are detected using classical statistical tests and machine learning models. Notably, the group lasso model is adopted because of its ability to extract group-based discriminative features that could be a range of damaged cerebral cortex spanning multiple brain ROIs. The analytics results in feature wrangling, detection, and brain network construction are finally integrated into the same visualization design for network comparison. The design natively supports both univariate and multivariate connectivity feature comparison in a multi-view interface. The first row gives the univariate comparison view showing multiple connectivity features. The comparison can also be arranged on the same feature but between multiple subject group pairs as shown in the second row. The multivariate feature comparison view in the third row allows to compare between different multivariate feature selection, models, and parameters. Our comparison visualization design supports versatile comparison among features, network connectivities, and subject groups. Still, multiple comparison results can only be displayed side by side. The trending patterns over time and the correlation of multiple features on the same network connectivity cannot be clearly identified. To address this high-order network comparison problem, we propose a brain necklace visualization design, which draws multiple features of the same connection as pearls on the network edge. A key challenge is to lay out the feature pearls and avoid heavy overlap. We designed a layout algorithm based on the principle of cost minimization. Moreover, we introduced a focus plus context interaction. We revisited our pilot study users and reported their findings in their case studies. With our system, the experts quickly identified the effectiveness of diffusion features as biomarkers to distinguish AD patients and healthy controls. They also find that if the data quality wrangling is not applied, the differences in those features are less salient. These are more visible in the connections between the brain hemispheres. The experts can also drill down to detect individual local biomarkers for AD patients. In a high-order composite view showing all the 4 diffusion features, 3 ROIs are identified with significant differences in all the 4 features. This connection is expanded in the voxel-based comparison in panel D. It is found that the healthy controls have increased FA values on the fiber tract, which corresponds to decreased or damaged fiber in AD patients. This connection is known as part of the corpus callosum, which confirms with the clinical evidence on AD degeneration biomarkers. On the other hand, the experts also examined the geometric features and tried to visually identify similar biomarkers for AD diagnostics. Unfortunately, no consistent progression pattern is found across diagnostic groups and age groups for all geometric features. This finding may imply that the destruction of white matter in AD patients' brains happens mostly on a microscopic scale. In conclusion, we propose a visual analytics system for uncertainty-aware multivariate brain network connectivity feature comparison and biomarker detection. The system is supported by multiple new techniques on data wrangling and network comparison visualizations, and evaluated on 2 real-world brain network biomarker detection scenarios. Thank you for listening.
And while we bring the speaker up, if you have any questions, please submit them on Slido. Hello, can you hear us?
Yes.
Wonderful. So maybe I get started with one question. I was just generally wondering, what are your thoughts on future work? Do you already have some next steps you want to work on?
Sure. Thank you, Johanna. For future works, I think, let me see. The framework we propose actually now work on structural brain networks, but we believe it could be also applied to other brain network modalities. For example, the very popular functional brain networks, on which we have more data, because structural brain networks we only have quite a few, very few diagnosis group networks, because it's very hard to measure some people with neural disease. But for functional brain networks, we have quite more data, and our framework and visualization, as well as the processing technique, can be applied. But on the functional brain network, maybe some more research should be focused on temporal analysis, because we now focus on the comparison between different categories, but we do not treat this category variable as sequential variable. We treat them as category 1. So additional work may be done on the temporal connective analysis using our framework.
All right.
So,
thank you. And then Marco Agus has another question. He says, excellent work. How heavy is the pre-processing stage?
I think it's a pretty good question, because what you see here is a PowerPoint presentation, but behind that, we have maybe many months effort on processing the data. Thanks to our members from our joint team across multiple institutions. Previously, we have built quite a few visualization tools over brain networks that already been processed and calibrated by domain experts. But in this work, because we want to examine the multimodal brain network connectivity beyond this strength connectivity, so we need to rebuild brain networks from the raw MRI and detailed data. To do this, we need to learn a lot of domain knowledge. In addition, we also conduct shape analysis and the diffusion metric analysis on the brain fibers, which is previously not considered for microscopic brain network visualization. In fact, these are not extremely hard, but definitely it's not trivial.
Thank you very much. Let's thank the speaker again.
Thank you.
All right, our next speaker is Said Bourbour from Stony Brook University, and he presents a talk called Neuroconstruct 3D Reconstruction and Visualization of Neurites in Optical Microscopy Brain Images.
Is this on? Good morning, everyone. Okay, so let's fire up our neurons for this morning session. So I'm presenting this work on behalf of my co-author, Parmida, and this work is in collaboration with the National Institute of Neurological Disorder and Strokes and the National Institute of Mental Health. As we will be listening to in this session, and we saw in the previous talk, really understanding neural connections that underlie brain functioning is central to neurobiology research. And recent advances in imaging modalities have made it possible to retrieve images of brain samples at millimeter, micro, and nano scales. And so using these images, the field of connectomics and relevant studies in image processing have made it possible to develop methods for the reconstruction, visualization, and analysis of neuronal connections and their maps and 3D structures. As we saw in the previous talk, it was more of a millimeter resolution for functional imaging. We focus more towards, and to really study the structure and connectivity and synaptic activity. Neuroscientists use micrometer, that is optical microscopy, or nanometer resolution imaging from electron microscopy. Our work focuses particularly on micro-resolution, that is optical microscopy. And we address two critical challenges that neuroscientists face in their workflow using optical microscopy. So for the first challenge, given its design, optical microscopy produces images by collecting light from tagged samples emitted from all layers of its 3D volume. And so the acquired images really suffer from degraded contrast between foreground and background voxels and low signal to noise ratio. And so really the out of focus light swamps the information that is required. So naturally, the first idea would be to segment these structures within the 3D volume. Next, so in a standard workflow, if you take a few steps back, what happens is a specimen is, the brain sample of a specimen is physically sliced, and it's laid on a glass slide for imaging. And so because of that, consequently, each brain is imaged and analyzed separately. So what is needed is a complete reconstruction of the brain from these individual sections so that we can enable a more wholesome understanding of the complex neuron morphologies and also to be able to use them to support visual analytic frameworks. So to this end, we have developed this toolkit called Neuro Construct for the segmentation and registration of neuronal structures in optical microscopy. For reference, in these images that I'm going to show you, these green blobs are the cell bodies that we're going to segment, and these thin fiber-like structures are neurites. At the optical microscopy level, we cannot really clearly identify the difference between axons and dendrites, but however, these fibers are the neurites that we're looking at. So let's first with our segmentation challenges. To segment these structures for qualitative and quantitative evaluation, neuroscientists have to eliminate background noise, as you can see in this image. So what they do is a very rudimentary approach, which is thresholding. And as you may have noticed, what happens is because of thresholding, we remove some of the thin fibers or low-intensity fibers in the attempt to remove the background noise. And also not just that, but because light adds onto each other, the out-of-focus light, some of the background is still in the volume, which has not been completely removed. So naturally, this means that we need a segmentation algorithm. Moreover, we also tried neuron tracing algorithms, but because of the blurring effect, because of the out-of-focus light, neurite tracing algorithms are not very effective to remove, to segment these structures. So, of course, we called upon the higher powers of deep learning, and we came up with a CNN-based model for automatic segmentation of the neuronal structures. Now, of course, we need ground truth data, and it's a whole process getting scientists and people to really annotate for us these ground truth data. So we came with this two-tier approach, and for that we generated this toolbox to really aid people or scientists to annotate structures for us. And what was challenging for us was, again, even with the toolbox, to really allow them to annotate in 3 dimensions. So what we realized is if we carefully examine the 2D views of the XZ and YZ strips, we could find this focus, a blob within the sweet spot within these sections where you can simply annotate and which we could use for training our segmentation model. So for the first year, we used crowdsourcing and we used domain scientists and asked them to just really color the center of this point spread. And we use a simple CNN model to generate just a lot of 3D annotations. So now the task was pretty simple. What happened was with training these 2D strips, we were able to reconstruct 3D volumes and ask them to use the toolbox to just correct these annotations by erasing or adding or editing, which was more a simpler task than simply having to annotate in 3D volume. And so to assist these annotations, we, among many other functionalities, we provided 2 particular brushes that they were interested in. One was the snap. And what that is simply, using snap, users could brush over the 2D structure in the XY plane, and the annotations would automatically snap on the highest intensity voxel. Here's a simple example. As you can see, the brush, you would just draw over the neurite, and it would snap onto the high-intensity voxel. However, this is used for non-overlapping neurites. And then for the next kind of brush, we used optical flow to automatically trace along the voxels of high consistency. And so this really speed up the process. What you would do is just click on one neurite, and it would use optical flow to go through the 3D volume and annotate automatically for consistent voxels. And so using all these 3D annotations, now we were able to come up with a nice CNN model to automatically segment our structures in the volume. For details about these structures, please refer to our manuscript. And so now, here's the result. You can compare the raw volume using thresholding and using our segmentation model. Now, segmentation is binary in nature. You have segmented and non-segmented. So the idea was to further allow exploration. And so we came up with this thing called hybrid volume rendering for further investigation. And specifically what we did was we converted the probabilities from the CNN model into a transfer function. So using a raw volume, you would pick a segmentation score for thresholding, and we use that to render in isosurfaces. And then for volume rendering, we would have a 2D transfer function for voxel intensity versus segmentation score. So by drawing over this 2D transfer function, we were able then to allow further exploration of the features. And so a recap, we have introduced a segmentation component of Neuro Construct, and now we move on to our registration pipeline. Briefly, it is a coarse to fine model. Coarse because, again, because these were randomly placed on a glass slide, we had to bring them coarsely registered on top of each other. And then at neurite level, we need to align the neurites across each section, the interfacing of each slice. So for the course, we employ MATS mutual information method for the middle slice of each 3D stack. And so this would free us from any limitations based on intensity-based registration and all that. And so we could just first have a coarse registration model. For fine registration, we utilize a trajectory of the neurites that are at the interface of each slice, so exiting or entering neurites. And we then convert them into vectors representing trajectories of their entry and exit. And why we do that is because while physically sectioning the brain sample, there can occur deformation or shear or loss of these biological samples. So there is this uncertainty around the interfacing slices. So then we project this trajectory for each entering and exiting sample. And we extrapolate it by generating this ellipsoidal tensor of trajectories. Excuse me. And then finally, we estimate an affine transformation for the 2 successive sections by maximizing the overlaps. So while this is showing you for a single neurite for the whole brain volume, we maximize ellipsoidal overlaps across all the neurites, all neurite pairs in the volume. And so we also allow them to verify this. If there are any incorrect alignment, they could use our interactive function to click and interact. And then we will concatenate the result through the remaining slices, propagate it. And so with that, I would like to thank you for listening to our talk. For, again, details on the model, the algorithm, please refer to our manuscript. Thank you.
Right, thank you much. Thank you very much for this nice presentation. I have a question to get started. I was wondering, do you retrain the segmentation model every time the user annotates something more?
Thank you. So we do have the option in the 3D annotation, the 3D annotation part. So when they're correcting the annotations after a first step, they can retrain every time, and so it improves as you retrain them. And because we're iteratively learning, it doesn't take that much of time to retrain the model.
Thank you very much. Then I would say, for the sake of time, let's thank the speaker again. Our next speaker is Chun-Young Choi, and he's going to talk about DXplorer, a unified visualization framework for interactive dendritic spine analysis using 3D morphological features.
Good morning, everyone. I'm Chun-Young Choi from Korea University. And firstly, I would like to thank our collaborator Sang-eun Lee, Eun-ji Chu, and Sung-woo Jang from Seoul National University College of Medicine, and my advisor Won Ki-jung. Today, let me introduce our work, DXplorer, a unified visualization framework for interactive dendritic spine analysis using 3D morphological feature. A dendritic spine is a protrusion attached to the neuronal dendrite. This structure plays a role in exchanging neuronal signals with other neurons. The ability of the signal transmission is closely related to the morphology of the spine. This is the confocal microscope image of neural dendrite. The spine morphology is characterized by a head part and neck part. Many previous papers have classified the spine into 4 phenotypes based on this nature: Philopodia, thin, stubby, and mushroom. As spines are a very dynamic structure, its morphology continuously changes over time. And the highly dynamic and heterogeneous nature is closely related to neuropathic pain or neuropsychiatric disorder. For example, it's known that an increase in neuropathic pain leads to an increase in mushroom-type spine. And spine number, density, size, and length can be an indicator of a neuropsychiatric disorder. Therefore, morphological analysis of the dendritic spine enables an understanding of brain function. The conventional dendritic spine analysis mainly goes through this process: spine detection, constructing of analysis information, and interactive analysis. However, in the past, only simple morphological features such as length, volume, and density have been used for analysis. Also, phenotype classification is performed through predefined metrics without user interaction. These are insufficient for proper analysis because spine have a highly heterogeneous morphology. In addition, there is no system can perform all of this analysis process, so analysts have to use a code-based program or a combination of multiple tools. This is a major bottleneck in the analysis workflow. To address this issue, we need to design visualizations can enable accurate phenotype classification while utilizing the expert knowledge, and a visual analysis framework can effectively unify the entire analysis process. To build a framework, we collaborate with 2 spine analysis experts. We had a regular meeting over a year and generated these task requirements. These requirements can be summarized into 3 keywords: construction of a unified framework, efficient data exploration and analysis, and accurate phenotype classification. As a result, we introduced DXplorer. This system mainly consists of 3 parts. A data management panel allows users to build and verify data sets from images. A visual exploration panel can perform data exploration and interactive phenotype classification. And group comparison panel can perform a comparative analysis between groups. Now, let me introduce each task in detail. Previously, in Kashiak-Geller's study, an automatic 3D spine detection method was introduced. However, since this method is provided as a code base such as MATLAB and Python, it was hard to use for domain users who are not computer major. To address this issue, we enabled to unify all required tasks in the visual interface. Here, the user can load the neuron images, select the ROI, adjust the image signal, detect the spine, and verify detected spine and features. Next, a morphological feature set was constructed from each detected spine object. In the past, 2D-based feature and 3D-based features are introduced. However, these are insufficient to properly represent the spine's 3D and complex nature. In this system, we constructed a novel 11-dimensional morphological feature set specialized in dendritic spine morphology. These spines have different phenotype, but the shapes are difficult to distinguish by conventional features. But our new additional features can easily distinguish these spines. In addition, we provide in situ features users can create interactively. First, the user can interactively detect synaptic regions and use the region as an analysis feature. Second, we provide a method to interactively create new features by combining existing features. This approach can enable more flexible analysis. With the constructed feature set, users can perform data exploration in the visual exploration panel. There can be dozens or hundreds of spine objects, even in single dendrite. So it's quite an inefficient and labor-intensive task to check and analyze such a large amount of data one by one. For more efficient data exploration, we propose an interactive 3D mesh grid view. Users can create a subset of the spine object through interaction in the parallel coordinate plot and 2D projection plot. In the 2D projection plot, 11-dimensional features are projected in 2 dimensions through projection methods such as PCA, TGNI, and UMAP. The grid view on the left of the interface is ordered through the generated subset and projected position. To do this, we constructed a 2D binary space partition tree in the feature projection plot. Then each leaf node of this 2D BSP tree is mapped to the grid layout. This ordered grid view can provide data trends. This approach makes it easy to analyze large amount of data intuitively while showing overall data trends. The criteria for determining the phenotype of the spine may vary depending on the data set. Therefore, it is difficult to perform accurate classification with a predefined metric or pre-trained model. To address this issue, we propose an interactive classification method. The user can find incorrectly classified spines through interactive exploration with the grid view. The user can include these spines with the correct label to the training set and retrain the machine learning classifier with the spine's morphological feature. The trained classifier performs classification again on the entire data. Then user can get correct spine types. This method enables fast and accurate phenotype classification while effectively utilizing expert knowledge. Finally, with the generated features, the users can analyze phenotype changes and feature differences based on the groups. To verify this framework, we performed a case study on actual analysis scenario with the expert. The goal of this study is to analyze the spine morphological changes by chemical long-term potentiation. In previous study, it is known that the spine head part grows normally when CLTP is treated on normal neurons, but the head part does not grow in the NALGPP2 knockdown neurons. To verify this, we conducted a morphological analysis with the dataset before and after the CLTP treatment. First, we created 2 groups representing before and after CLTP treatment and loaded the dataset into the group. The phenotype of the added spine is classified by pre-trained machine learning classifier, and we found incorrectly classified spines through visual exploration and retrain the machine learning classifier by adding them to the training set. During the case study, we added this spine to the training set to retrain the machine learning classifier, and the analysis results show that the head part does not increase significantly, so the machine type spine number reduced. With this study, we could successfully compound the result of a previous study. To conclude, in this paper, we proposed the Explorer, which is all-in-one system for dendritic spine analysis, and enable accurate phenotype classification and various analysis. In the future, we plan to make system applicable to other microscopy imaging modality and analysis tasks. Currently, the Explorer is already being used in various research projects. It is being actively used in real research on dendritic spine analysis. Also, it is being actively used in other research fields, such as analysis of morphological changes of kidney cell and analysis of morphological change in substructure of ears. Thank you.
Thank you. Great work. I was wondering, what's the feedback from the domain scientists? Like, are they actively using this? What's their favorite feature? Is there anything that they find particularly useful?
Okay, thank you for the question. Actually, our collaborator enjoyed and can utilize all of the many functions in this system, but I think they mostly like the unified visual system from feature generation to visual analysis. In the past, the biologists should perform each analysis task using multiple tools or code base. So also they should learn some programming language for that. So it is quite hard to them. So, but thanks to the Explorer's unified system, they can focus on their own essential research, I think. Yeah.
Wonderful. Thank you. So our next presentation is by Chao-King Xu, and the talk is a predictive visual analytics system for studying neurodegenerative disease based on DTI fiber tracts, and it's a virtual presentation.
Hello everyone. My topic today is a predictive visual analytics system for studying neurodegenerative disease based on DTI fiber tracts. The researchers use diffusion tensor imaging for brain fiber tracking to obtain the brain fiber bundles of human brain, and then infer human brain connectivity to provide brain disease analysis. The research of brain fibers generally includes DTI fiber tracking, fiber tract visualization, disease fiber analysis, and predictive fiber exploration. A lot of studies have shown that the techniques of fiber generation, visualization, disease analysis, and predictive techniques have gradually matured. But since brain fiber data is large-scale, high-dimensional, and multi-level, currently there is no engineering framework to systematically explore fiber integrity in brain disease. Thus, we set our design goals as 4 aspects: the exploration of high-dimensional features, the visualization of fiber microstructure, multi-level comparison, and systematic exploration. Based on the design goals, we developed the brain fiber visualization system. The core of this system is a machine learning pipeline. The input of the machine learning pipeline is the feature matrix of each brain region. The core is binary classification in each fold of k-fold cross-validation, and the outputs are feature scores, region scores, and subject class probabilities. Here we show a demo of the brain fiber visualization system. It contains 5 modules: the cohort selection module, the machine learning module, the interface for saliences and predictions, the information visualization module, and the 3D fiber rendering module. The user begins by selecting cohorts through a module that balances the subjects in each group while stratifying with age and gender, and fill in the age and gender distributions of both the healthy group and the disease group. Next, The user initiated the machine learning pipeline with input parameters and then executed the machine learning pipeline using a selected classifier. The user can facilitate a wide range of subject-level comparative analysis through the 3D rendering fields and the linked information visualization fields. The compared subjects are based on selections from the subject prediction field. The user can select the subjects based on the average predicted class probabilities and gain insights into the important physical patterns. Through intuitive visual comparison of multiple subjects, the user can have a better understanding of the different physical patterns between the healthy group and the disease group, and employ knowledge to form a new hypothesis. The user can easily select between features and subjects in a programmatic way, can easily grasp the wider context, and maintain a strong sense of awareness about the involved uncertainties. This approach can benefit neurodegenerative disease researchers by helping them more easily obtain a wider perspective into their data. The region that is rendered is automatically selected based on the user's selection from the region importance field, and the color mapping is based on the selected features from the feature importance field. The radials can be interactively adjusted to help reduce or increase observable details in the physical space. And the 3D rendering fields supports rotation, zooming, and panning operations. The user can also toggle between the whole brain colored by the feature and inspect the disaggregated features as they are distributed on the whole brain fibers to look for patterns. The analysis space is divided into three primary modalities: spatial regions, statistic features, and individual subjects. They can each be toggled between plot fields and table fields. The values displayed include average and standard deviation of the estimated saliences and predictions. The information visualization module contains several fields. The parallel coordinates field compares distributions of feature trends across groups. The scatter plot field gives insights into the relationship between a feature and the classification module. The trend field gives insights into group differences and the statistic quality of the data. The dimensionality reduction field gives insights into which subjects are more similar to others in high-dimensional space. The covariance matrix field supports bivariate dependence analysis, helping in the understanding of feature correlations. Group trends in age and gender show the progression of the feature as well as the differences between groups. The customized interactive visualization fields are directly linked with each other. This gives a better context to the observed differences and uncertainties. We then conduct case studies. The data is from the PPMR database, which is an open-source database for Parkinson's disease. We explore fiber bundles with streamlines starting from the substantia nigra region, from which we got prior knowledge from experts. Our focus is on trends with age and on spatial feature patterns from the elderly subgroup. From this figure, we can see that there is a brain fiber loss in the diseased brain, which shows more blue bundles. Also, their theory features show different spatial distributions on the healthy and the disease group. In addition, we see a clear drop in average fiber length in the elderly Parkinson's subjects, while the average fiber length of the healthy group maintained constant. The figure also shows the association between average fiber length and age for gender. We see a clear drop in average fiber length in elderly male subjects with Parkinson's disease. After that, we also provided a data-driven case study, which analyzes the data while fully utilizing the salience measures produced by the system, and do not rely on assumptions from past knowledge. Since our system indicates the best predicted region of Parkinson's disease is fusiform region, we provided an analysis of the top performing features, detailed patterns, and then trends with age and gender in this region. We found that some healthy subjects with a low mean MO trend to have more fibers around the area annotated with dashed black ellipse. Some Parkinson's subjects have fewer fibers in the area annotated with the green arrows. The Parkinson's group has a higher MO feature than the healthy group. The trends of the male and female subjects also show different patterns. We totally involved 5 experts in our study. We conducted live interactive demos and shared a draft of our manuscript with 3 experts, and then assimilated the feedback into our design and the paper. Another 2 experts were then helped to evaluate our system. The experts indicated that our work is innovative and useful, and can be used as a tool for qualitative analysis of brain fibers. However, limitations also exist. The first is computational cost. With a high-performance workstation, the generation of each brain takes about 12 hours, and the storage is about 4 GB. Also, fiber tracking algorithms are constantly updated, and the fiber-based disease analysis is still at an early stage, which brings some difficulties for experts to draw conclusions. At last, let's make a conclusion. We developed a brain fiber visualization system to help neuroscientists study brain disease, provided a machine learning-assisted visualization pipeline to narrow down the large information space, offered an analysis workflow helping experts interactively explore their data. And in the future, we would like to conduct collaborative analysis of fibers or features in multiple brain regions, and develop new strategies to localize and evaluate abnormal patterns of disease fibers. This is our report. Thanks for listening.
Thank you very much for your presentation. We have time for one question. And Marco Agos is asking, great work. Did you consider some ways to represent the difference between the 3D views to highlight patterns and areas?
Yes, great questions. I'm actually trying to figure out some way to highlight the disease patterns in 3D views. So this is what I'm trying to do in the next paper. And actually, this is my first work on brain fiber tracks. I have been done some work to make a prototype system that I can cooperate with doctors and neuroscientists. Then this is the starting work of the project.
Thank you. There's actually another question, so maybe you can go to Discord and answer that other question, because for the sake of time, we have to move on to the next speaker. But thank you again. Let's thank the speaker. So for our next talk, we welcome back Saeed Bourbor, and he will talk about Neurogenerate, a framework for visualizing neurodegeneration.
Thank you. Oh. Okay. Thank you. So this is work, again, by the same group in collaboration with NIH. And it's so nice to see that in this session, following that functional millimeter resolution, now we go back again to microscale resolution. So similar to the previous work, I am here to introduce a framework that we've developed called Neurogenerate, which we have designed for visualizing the degeneration of neural fibers. And again, as we've seen in this session, high-resolution data acquisition systems coupled with visualization techniques have really aided the field of neuroscience to make significant advances in really understanding the brain physiology and structure and functioning. So like the previous paper, of particular interest to our collaborators is also the study of neural fiber integrity during, in our particular case, aging and diseases that cause cognitive decline. And so consider the case of analyzing change that occur in neural fibers across aging. Unlike, again, the previous work where it's non-invasive, in our workflow to visualize these neuronal structures, a sample has to be sacrificed and the brain has to be physically sectioned, placed on a glass slide, labeled and imaged, in our case using optical microscopy, and then employed for visualization techniques for qualitative and quantitative evaluation. So naturally, in contrast, in our work, one specimen can only be imaged for a single time point. So now the comparison is challenging. So what happens is, as a result, in order to really understand the differences, to understand the progression of change, a population of subjects from each domain is needed. And only generalized observations about the state of the fibers across the time points can be made. And so, for instance, by imaging and qualitative analyzing the collection of data sets, a scientist may note that these fibers become thinner and more fragmented as the brain ages, as shown by the red arrows. And so now what is needed is a visualization to study the profile of the neurites at more of an individual level or within subject analysis. And so to this end, we have designed and developed a framework which we call NeuroGenerate for the prediction, reconstruction, and visualization of changes that occur across that occur in neural fibers across age. And we've designed NeuroGenerate based on the requirements of our domain scientists. And so for this talk, I will cover two fundamental challenges and goals. For the first goal, given an input brain volume of any age time point, what is needed was this framework to predict a plausible morphology for a future or past age time point for these neuronal fibers. And so again, going back to the workflow, the challenge is we do not have ground truth data, or we do not have one-to-one correspondence to train any model. But again, calling upon the powers of deep learning, we drew our model based on CycleGAN. So briefly, just to give an idea, CycleGAN is an architecture that is designed specifically for solving image-to-image translation where there are paired correspondences. And, where paired correspondences are not available. And so what happens is there are two individual generative adversarial networks that learn the translation of features from one domain to the other. So in this example from their paper, it's from zebras to horses, for example. At its core is this idea called cycle consistency loss. And what that does is it ensures features correctly translate or reconstruct after being translated from one domain to the other and back. And so this loss is what really learns the features between the two domains. Now, we extend CycleGAN for our framework's deep learning model, which we call NeuroGenerator. And while CycleGANs have shown impressive results for style transfer, it, however, does expect a one-to-one translation of features across the two domains. Whereas in our case, when translating from young to old domain, the fragmentation or the loss of neurons can have multiple solutions. So for that reason, we imposed this thing called the additional extended cycle consistency GAN. And so what that is this loss when applied to young to old domain, it ensures that our modality not only learns the reconstruction of young features and back, but also imposes an additional loss on reverting back to the old domain. So this ensures that we can have one-to-many learning of features across the domains. Among other things, an additional novelty to our work would be to extending CycleGAN to volume. In the original CycleGAN, it's image-to-image. We extend it to volume domain translation. In general, one inherent drawback of CycleGAN is this appearance of phantom artifacts in the prediction output. So we address this by introducing a new loss called hallucination loss. The details, for details, please refer to our manuscript. But it restricts the predicted features to remain conservative based on structural features that we can only see in the domain. So it's just like it's imposing an additional loss to the training part. And so finally, like many deep learning algorithms, due to commodity hardware and its memory limitations, working with large volumes such as the brain, requires the data to be split into smaller chunks. And so this can hamper the learning of connectivity, or when we stitch back together individual tiles, it can cause tiling artifacts in the whole large volume. So for this, we introduce a novel spatial consistency architecture in our model. Again, for details, please refer to our paper. And now to take a look at some of our results. Here you see a cropped section of the medial septum region of the brain, which is the blue region in the top left corner. So here in this first example, for a 6-week young mouse, and its raw microscopy data in green, in red we render its predicted 9-month-old result. And likewise, for a 9-month-old data, in red we predict its 6-week young volume, which is shown in green. We'll come back to this result later for more case studies. So in this next example, I will show you the improvement in the reconstruction quality due to spatial consistency module. So given this 9-month input data, this is the result without spatial consistency and with spatial consistency. So with the blue arrows, you can see that we alleviate tiling artifacts. And with the yellow arrows, you can see we've even reconstructed the continuity of thin fibers across tiles. And so for our next goal with this, after this prediction component, would be to design visualization that will be able to directly compare the input and the predicted volumes simultaneously, and also visualize a time series representation of the degeneration or degradation of these structures. And so for that, we have developed an application that provides 2 visualization modules, Neuromorph and Neurocompare. Briefly, Neurocompare is designed to allow simultaneous comparison between the input volume and the predicted structure. For the input volume, you can use direct volume rendering and transfer functions and enhancement features, whereas we use the predicted volume as isosurface. And so the reason we do this is because the structure is synthesized, you can play with direct volume rendering for the raw input data, so the isosurface is just used as a reference, the prediction. So we don't influence really the result on the neuroscientists. For more illustrative and interactive understanding of the morphological change, we have developed this algorithm, morphing algorithm, that computes transformations between source and target volume. And input could be raw, and then our predicted volume. But specifically taking into account the vesselness or the tubular feature of the neurites. Briefly, for each neurite, we assign a path of voxels that exist in one domain to voxels that exist in both domains, and then form a linear transformation along the assigned path to reconstruct the in-between volumes. However, I would like to bring to attention here that this would be generated for 2 time points. If we want more granular or more precise results, we would have to train more in between ages to kind of have a more better granularity across the time points. So to recap, we presented a deep learning model for predicting the structure of neuronal fibers for past and future time point. And to visualize the changes in the profile of the fibers, we have developed 2 visualization application that allows, in 2 visualization modes that allows simultaneous comparison and a time series representation of the volume. So now for the case studies, NeuroGenerate is being used by neuroscientist collaborators to study the cholinergic system. And that's really the system that helps in memory recall or cognitive tasks. So, you go into a room and you forget what you were doing. That's exactly the degeneration that we were looking at. And so particularly, they're interested to see integrity of these fibers across aging and Alzheimer's. So for our case studies, they use 2 regions of the brain, 6 weeks and 9 months. As you saw in the results before, we saw one case in the medial septum region. And so using NeuroGenerate, the neuroscientists were able to confirm that, so previously there was this idea that cell bodies is the signal to show cognitive impairment. But now through NeuroGenerate, they found out that fiber thinning and fragmentation happens before overt signs of impairment. And so with this, they could even analyze the rate of fragmentation or the amount of fragmentation that happens much before the loss of cell bodies. So that was one thing. The other case study was in the cortical region of the brain. So there was this hypothesis that the fibers in the cortex is more resilient. While that is true, using NeuroGenerate and comparing it, they actually found out that they thin much faster and much before even signs of impairment. So using NeuroGenerate, we were able to now generate new hypotheses. That is now an area of study amongst our neuroscientist collaborators. To briefly go over some limitations and what we want to do with those limitations, as you could guess, NeuroRegenerate is designed specifically on the requirements of our neuroscientist collaborators, and particularly for thinning and fragmentation. We want to see what are some features beyond just thinning and fragmentation. I know inflammation or branching, or to study what are some other features, make it more general. And then secondly, although we only study two particular regions, the medial septum and cortex, what we want to do is make a whole brain analysis. So any feature or any part of the brain, we have some spatial correlation, and we can study the progression of these changes across any region of the brain. And so with that, I thank you. Again, please refer to our manuscript for more details.
Thank you very much, Said. Marco Agos posted a question. He says, amazing work. My question is related to extraction of statistical shape features. Are you planning to do further shape analysis to find insights?
Yeah, that's very interesting. Thank you. So that's what one of the limitations that I was referring to is right now our features are only thinning and fragmentation, but we want to look at other shapes and features. For now, we kept our model very conservative just to be sure that we're generating plausible enough morphologies, because then the question is, are we seeing hallucinations or not? But we would want to do more rigorous evaluations based on other geometrical features. Our biggest challenge is that we do not have ground truth, right? Because you slice a brain once, we cannot really tape it back. So it requires a little bit more research. But yes, we're looking into other geometric features that we could learn.
Thank you very much. Let's thank the speaker again. All right, so let's move on to our last speaker for the session. The presenter is Monique Moischke. The talk is titled Gucci, Guided Cardiac Cohort Investigation of Blood Flow Data.
Welcome to our talk. Today, we present Gucci, a framework for guided cohort investigation in terms of measured blood flow data. Cardiovascular diseases are correlated to abnormal morphological and hemodynamic features. Four-dimensional phase contrast magnetic resonance imaging, or 4D PC-MRI, enables non-invasive acquisition of time-dependent flow data in a volume. Several groups developed visual exploration techniques for single 4D PC-MRI datasets. Visual analytics support for analyzing cohorts is needed to improve the diagnosis of CVDs, to assess their severity more reliably and to support therapeutic decisions. Therefore, we introduce the framework Gucci that enables a comparative visual analysis of multiple 4D PC-MRI datasets. We will focus on aortic blood flow and related pathologies for predefined cohorts. Gucci comprises multiple linked views to comparatively analyze cohorts, where the user's attention is drawn to interesting features. In cooperation with the Heart Center Leipzig, we have measured blood flow data from 90 healthy volunteers and 30 patients with a bicuspid aortic valve. This is one of the most common heart valve defects. While a healthy aortic valve consists of 3 leaflets, 2 of these leaflets are fused in a bicuspid valve, which leads to a change in the flow characteristics and can trigger secondary diseases such as aortic aneurysms. To extract features from the measured flow data, we use the software bloodline. Basically, 2 types of features are distinguished: global features, which refer to the entire vessel, and plane-based features that are computed on 6 predefined measuring planes arranged orthogonally to the centerline in the aorta. Moreover, both feature types can be static over the cardiac cycle, called time-independent features, or change during the heartbeat, called time-dependent features. This results in 4 classes of features, with most features falling into the global, time-independent class. In this work, we focus on the visual analysis of 3 predefined cohorts: healthy volunteers versus bicuspid valve patients, older healthy volunteers versus bicuspid valve patients, and female versus male healthy volunteers. The aim is to investigate whether there are characteristic features that distinguish healthy subjects from bicuspid valve patients. In addition, our collaborating physicians were interested in whether older healthy subjects show similar flow characteristics as bicuspid valve patients. This could help to assess the severity of bicuspid valve. In addition, the question arose whether flow characteristics differ between women and men. Since we have 197 global, time-independent features, we first applied different selection techniques and classifiers to reduce the number of features. Due to the complexity of the data, we first provide a qualitative overview to assess the separability of cohorts. A frequent procedure for visualizing multivariate data is to apply dimension reduction techniques. Standard techniques such as scatterplots can be used to depict the projected datasets. Based on this concept, we created a 2D cohort atlas, where the pre-selected global time-independent features serve as input. We used a map for dimension reduction. Each data set is represented by a colored circle, where color reflects the cohort. Here, orange indicates BOV patients, while green represents healthy volunteers. The background color represents the density distribution of the data sets. In dark gray areas, many data sets lie close together, while a light background depicts sparser regions. In addition, individual datasets can be brushed in red, which are then also highlighted in the upcoming views. Starting from the 2D atlas, the user can study qualitative and quantitative differences and similarities of time-independent features between the cohorts. For this purpose, parallel coordinates and statistical diagrams are provided. In the parallel coordinates, the lines are colored according to their cohort membership, which can lead to visual clutter as you can see in the picture above. Therefore, we apply a line bundling technique, which leads to a group representation based on a density-based clustering of the polylines. Since the line bundling cannot completely bypass occlusions, we applied transparency to the bundles. This communicates the frequency of the data sets with certain feature values by overlaying several transparent bundles. In addition, the statistical diagrams on the right provide more insights about the distribution of two selected features. Both features are visualized using a scatterplot where we determine if a linear, quadratic, or logarithmic relationship fits the underlying data. Moreover, marginal histograms display the distributions of the features as univariate histograms on the horizontal and vertical axes of the scatterplot, respectively. To explore the 17 time-dependent features, we adapt a heat map to give an overview, called pixel plot, as shown on the left. Each row represents a time-dependent feature, where the columns represent the measured time steps. A pixel plot is drawn for each cohort. Within the cohort, the mean value of the respective feature is determined for each time step. These mean values are normalized across all cohorts and are mapped to a light to dark purple scale. In addition, the shape of the primitives indicates discretized ranges of the standard deviation to provide further statistical insights. To filter an interesting feature, the user moves the mouse over the pixel plot, where the corresponding feature is highlighted in all pixel plots. For a selected feature, a line plot is adjusted, which shows the temporal course of the datasets. The lines are colored in relation to their cohort. The red line indicates the currently selected time step. Similar to the global time-dependent features, we combined a space-saving overview visualization with a more quantitative view to depict the plane-based features. Inspired by cartographic map visualization, we use hexagon plots, where each feature is represented by a hexagon. Each triangle within a hexagon represents one of the 6 planes, with its colored border matching the plane colors. Within the triangles, the cohort mean value of each feature is color-coded. The hexagon plot is used to quickly locate features that are very similar or different between cohorts in terms of the measurement planes. For a more detailed investigation of the diversity of selected features, parallel coordinates are shown to the right of the hexagon plots. The vertical axes correspond to the 6 planes. To depict the time-dependent features, we also used a visualization in which each plane is represented by a partial geometry. The temporal progression should be represented statically to avoid perception problems with animations. Therefore, we used violin plots, where each plot represents a cohort and each violin represents a feature. Each arm of a violin corresponds to one of the 6 measuring planes. The measured time steps are plotted along an arm from inside to outside. Dark purple wide areas represent high mean values and thin light areas show time steps with low mean values. To examine the temporal course of a feature at the planes more detailed, a line diagram adapts itself besides the plots. This shows the temporal behavior of a selected feature at a specific plane. When the user moves the mouse over the arms of the violin plots, the line diagram adapts. To further support data analysis, we integrated different ways to direct the user's attention to strong dissimilarities between cohorts. On the one hand, the glyphs in the pixel plot and in the plane-based visualizations can be ordered regarding dissimilarity between cohorts. Moreover, dissimilarities can be highlighted in the corresponding line plots. Therefore, we compute absolute differences of the mean values over time between 2 cohorts, which results in the blue dissimilarity curve. Afterwards, we separate this curve into regions using the local maxima. Finally, an average difference value is calculated for each region, which are color-coded. Thus, the user can immediately see in which temporal areas strong differences between the cohorts occur. To check whether Gucci is suitable to support a comparative analysis of measured blood flow data, we performed a prevalence study with 3 radiologists. The physicians detected clear differences regarding the global and plane-based features between 2 cohorts. According to their expectations, for example, the maximum flow velocity, vortical flow volume and pressure values in BOV patients are about 2 to 3 times higher than in healthy volunteers. In addition, BOV patients have a lot of increased values regarding the global time-dependent features, which shows the increased pumping capacity of the heart due to the valve defect. However, Against their expectations, the healthy volunteers show large variances in the time points, where the maximum in-plane velocity and vortex volume occurs. To further explore these variances within the healthy volunteers, the experts brushed healthy data sets in the parallel coordinates. The selected data sets are highlighted in dark green, which the experts then explore in the remaining views. Due to the similarity-based ordering of the features, the experts immediately find out that some of these healthy data sets show very high values for the global time-dependent features, for example, increased volume values of the right rotating flow. In contrast, however, these selected healthy data sets do not show particularly elevated values in the plane-based features, which was very surprising for them. The selection of conspicuous data sets helps the physicians to better understand the variety of flow features of healthy volunteers. In conclusion, medical experts are strongly interested in a cohort-based analysis of cardiac blood flow data to derive normal value ranges and establish medical guidelines. Gucci enables a detailed study of CVDs as well as the diversity of healthy volunteers with respect to aortic flow information. The user is guided through visual analysis of the complex data by highlighting strong differences and similarities between cohorts. With this, Gucci supports the assessment of disease severity and the interpretation of measured blood flow data. In the future, we want to integrate and visualize blood flow data in other heart vessels. Diseases, such as stenosis, also occur, for example, in the pulmonary artery. Moreover, in addition to quantitative flow properties, qualitative features seem to influence the development and progress of CVDs. Therefore, we plan to integrate the 3D vessel geometry and patterns of internal blood flow into the data analysis. Furthermore, we plan to improve the discovery of new, interesting cohorts based on the hemodynamic and morphological features. For this purpose, suitable clustering methods and interactive visualizations of the cluster results are required. With this, I'm at the end of my talk. Thank you for your attention, and I'm looking forward to your questions.
Hello, Monique. Thank you very much for this presentation.
Hi.
I have one question to get us started. I was wondering, can Gucci be used for the analysis of other vascular structures, and how much effort would it be to adapt Gucci for other vascular structures?
Okay, thanks for the nice question. So in general, Gucci can also be used for other vascular structures, but of course we have included several representations of the aorta. So this has to be adapted regarding the vessel that you want to explore. But regarding the numerical values, most of the visualizations could be reused also for other vascular structures.
All right, thank you. And then maybe one more question. As I understand it, Gucci so far has been used to analyze predefined cohorts. So is it also possible to define new cohorts with Gucci and analyze them afterwards?
So in the first version of Gucci, we provided the correlation matrix of all features where the Pearson correlation was color-coded. And with this, the physicians were able to first reduce the number of features. And then we used the interactive histograms to define new cohorts. But it turned out that this is not the best procedure. So the physicians had huge problems to really define cohorts by themselves. So this is why we want to include more techniques or more advanced techniques like clusterings to find or to support the detection of new cohorts.
Very interesting. Thank you very much. So let's
Thank
thank
you.
the speaker again. This brings us to the end of our session. So thank you guys for attending, and there should be a coffee break outside.